All right, chemists. Well, let's get started here. So anyway, welcome to this Sunday's edition of the masterclass in A-level chemistry. All right, looking outside right here as we record this one, it is indeed starting to snow. All right, so don't know where you are. All right, but it is indeed starting to snow, and let's see. All right, just making sure the technology is there up and running. So anyway, chemists, so I hope you're having a good week. And on this one, being asked by a few subscribers, would I mind going over redox reactions, and especially balancing redox reactions in acidic media and alkaline media. Okay, so what I want to do on this one then is quite simply, chemists, is I wanted to start off with a quick recap of redox reactions, as in oxidation states, okay, like oil rig. You probably learned oil rig at GCSE. So start with this one, and I'll give you a different definition of oxidation and reduction in terms of losing and gaining electrons. Then we'll look at oxidation states, and we'll figure out that oxidation states are variable for transition metals and non-metals, and I'll tell you why. Okay, and then we'll look at balancing equations in acidic media and alkaline media, and I'll show you how to combine equations, how to cancel out valence electrons and everything else. And if we've got time, and today is going to be kind of a packed one, to be honest, we are going to be, no, I just got to make sure I got this one going here. Got to make sure I'm on YouTube here, right, as well. All right. What we have to be then, chemists, is aware of the time. I'll try to get a past paper question in at the end, like I always do. All right. And that should wrap up this lesson on it. And what I'll do next lesson is I'll go over some specific examples. All right. We've got some good past paper questions we can do on the extraction of metals and the reduction of sulfur and everything else, all the good stuff that we normally include in these help sessions. All right. So without further ado, then, chemists, let's do this one. All right. Let me share my screen right here, and let's pop out to our good friends at BitPaper here. All right. We do like BitPaper because BitPaper is a nice solid product. You know, it's stable, it's solid, and now I found it, I just enjoy using BitPaper. All right, then. So, chemists, here we are in Air Force Blue. Yeah, this week is going to be in Air Force Blue, chemists. All right, on this one, then, let's look at redox reactions. And so, hold on, turn pen on. All right, redox reactions. Okay, so this week, and actually next week as well, we'll have an in-depth look at redox reactions. And of course, redox reactions are for my year 12 students, because the last couple of lessons, you know, master classes, we've been looking at year 13 topics. And so I said, right, you know, let's go back into year 12, help them out. All right, then. So redox reactions. Now, on this one, I know at GCSE you've done oil rig. All right. And so real simple. Always start off with what we know. All right, there's oxidation right here. And just love BitPaper. It's just a really nice, solid product right there. Yeah, is my reduction. You know, it's going to match up oil rig when we're done. Okay, like this. And we're thinking, all right. Now, this is what you learned at GCSE, right? You learned that oxidation is losing electrons. True. And reduction is gaining electrons, like this. And so this is what you learned at GCSE. However, you may think of it this way. Another way of looking at it, and this becomes really important or useful when we look at organic chemistry. All right, is this one. You can say that oxidation is gaining oxygen. So this one is useful. Specifically, two examples come to mind. First one is if you're looking at the oxidation of alcohols up to aldehydes, ketones, and carboxylic acids, well, then this is a useful way of looking at a redox reaction. All right, number one. Also, for example, if you're doing alkanes and you're looking at the oxidation of carbon and nitrogen in that module on alkanes, or the energetics module, all right, could be handy right there. So oxidation is gaining oxygen, and right here, then obviously reduction is losing oxygen. All right. So far, not too bad, just a couple of definitions, right? Now then, right, yes. But another thing we need to do when having a look at definitions then is, perfectly straight line there, is this one. All right, we need to have a look at, well, what exactly do we mean by oxidation state? All right, so oxidation state at GCSE, what you learned that there was a charge on the ion. All right, so ions hold on, try to squeeze that in a little bit better. Hold on. Ions have a charge. Okay. And so you're thinking a cation is an ion with a positive charge, and an anion is an ion with a negative charge. Right. And so the reason that I mention this bit is, let's get the definition in there, because then when you do electrochemistry and we start talking about cations and anions and electron transport, well then, yeah, you've seen the definition before, right? So here we go. All right. So sodium ion, yes, a sodium ion. Now this is the bit now, right? This is just quality of language. Sodium ion, is +1. And so at GCSE, you would have said sodium ion has a charge of +1. At A level, you would say sodium ion has an oxidation state of +1. Yeah. So in your mind, think you can take charge and just replace it with oxidation state. All right. It's a more fancy way of saying charge. So, for example, chloride. All right, at GCSE, you would say chloride has a charge of -1. And at A level, you would say chloride, the anion, has an oxidation state of -1. Right, so just some definitions before we do some calculations, all right? So we're thinking, yeah, we've got oxidation, reduction at GCSE. You learned as oil rig, losing and gaining electrons. You may have also seen it as gaining and losing oxygen. Ions, we say and have a charge. Cation is a positive ion, anion is a negative ion, and all you have to do is just swap oxidation state for charge. Right, so now then, the next question becomes this one. Well, what's this I've been reading? Or maybe my teacher's been talking about something called a variable oxidation state. Right, here we are. So a variable oxidation state, chemists, is this one. All right. If on this side, let me explain it like this. On this side, I got this. These are my fixed oxidation states. Right. Group 1. Sodium. Let's use sodium again, right? So sodium, all right, is neon 3s1. Yeah, so you notice how now what I'm doing is, what I'm doing now is I've tied it back into, I've tied it back into the electronic configuration. All right, so if you need to, go back into your notes and have a look at the electronic configuration. All right. So you're thinking, right, sodium is +1. Hold on there, folks. We have a few people trying to get in. Hold on. Let's have a little look. Okay, right. So let those in. All right, then, so look, group 1 then is sodium is neon 3s1, right? So therefore, you'd say, yes, it does make sense if sodium ion is written as neon, because there's only one, and let me do this in orange, there's only one valence electron. So absolutely, you'd say, yes, this has an oxidation state of +1, there's only one valence electron, Graeme, so therefore it is indeed true. It is a sodium +1. It couldn't be sodium +2, because you're thinking, well, sodium +2 would mean I'd have to break into that noble gas core configuration. No, that's not going to happen, right? Energetically unfavorable. Right. So having said that, group 1 then makes sense. And then if I come along and I look at, do this in orange, spice things up a little bit here. All right, group 2. I think you can see where I'm going with this one, right? So the main group metals, group 1, group 2. And so group 2, get rid of this and undo the ruler option there. So look, group 2. Right. Magnesium, same exact argument could be used, right? Magnesium is going to be neon 3s2. And so the ion is going to be magnesium 2+. So you're thinking, right, which is just going to be isoelectronic, the same electronic configuration as neon. Right. Perfect sense, right? Now, you're thinking it couldn't be a negative valence. It couldn't be a negative oxidation state. Hold on. We've got 2 valence electrons. it couldn't be a negative oxidation state, because that would mean, well, for neon, for magnesium, I would have to gain six more electrons. I have to fill up the p subshell. Energetically unfavorable. It's, you know, it's not going to work in terms of nuclear charge density, electron negativity, ionization energies, all that stuff you learned in the previous module is just not going to be working out, right? So you're thinking, yeah, group 1, group 2, and group 3. I'll do group 3 down here. We'll do aluminum right there, you know, like this. Group 3 like this. Yeah, aluminum is going to be, hold on, what, neon 3s2, 3p1. And so again, chemists, you're thinking the argument is, of course, aluminum has to be 3 plus, and so therefore it's just going to be, again, isoelectronic to neon, which means same electronic configuration as, quality of language right there. But again, 3 valence electrons. Yeah. So again, you're thinking, right. Now, makes perfect sense, right? And so group 1, group 2, group 3, yeah, they're all fixed oxidation states. On the other hand, if I took a look at, and let me do another orange line down here, like so. If you take a look at, chlorine, for example, we'll do chlorine real quick, right? Right, so chlorine is going to be, hold on, chlorine, is that what neon? 3s2, 3p5, right? Now, keep in mind, you're thinking, right, I've got 7 valence electrons here. And so what you probably learned at GCSE, hold on, 7 valence electrons. What you probably learned at GCSE, I can write valence a little bit better than that. Come on, right. 7 valence electrons, right. What you probably learned at GCSE is that, well, chlorine ion is -1. All right, so back into Air Force Blue, as I like to call it. Oh yeah, so the oxidation state, the charge on chloride is -1. And so you're thinking, right, this would be what, neon 3s2, 3p6, which is isoelectronic to argon. Yeah. But on the other hand, it could also, so chlorine can go from +7, hold on, I'll do this way here, I'll do -1 down here. It can be -1 up here, because I'm thinking number line, right? -1, which is the one that you always think of, all the way up to +7. And you think, what? I've never heard of chlorine being +7 before. The chloride being +7. Well, because at GCSE, the only thing they do, chemists, is that they tell you the most common charge, the most common oxidation states. But if you have 7 valence electrons here, I think you can either add a valence electron in and you can make it up to, you can fill the subshell, right? There was 3s2, 3p6. Or on the other hand, you can go in the other direction and you can remove all of the valence electrons. Yeah. And so, yeah, it wants to point this out because we'll do variable oxidation states now, right? But for example, chlorine can either be -1, you've seen that, all the way up to +7. All right, so for example, another one. I'll do one from group 4 because I think you can see where I'm going now. All right, so look, on group 4 chemists, all right, carbon. Right, carbon is helium. Doing all this from memory because I don't have a table right here. Helium, 2s2, 2p2, right? And so are you seeing that what you can do is that you can gain 4 valent electrons. So you could have carbon with a -4 oxidation state, which would be helium 2s2, 2p6, or on the other hand, you could have carbon be +4 because you could lose the 4 valent electrons, and this would be helium. So carbon has a range from, think you fill up the subshell, so it could be -4, back in Air Force Blue, hold on, -4, all the way up to +4. Yeah, just depending on, well, what it's bonded to. Okay, so we've done the ones with non-metals, and we've done the ones with metals. And hold on, chemists, let me see if I can get a periodic table up here because I wanted to do one more. I did want to do the one with a transition metal. So hold on. Let me pick a transition metal here. All right, so ding, 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 got it. Gotta love the internet, don't you? Right then, okay, so on this one then, chemists. So we understand it, right? You're thinking group 1, group 2, group 3, the main group metals, fixed oxidation state, nothing strange there. Seen that before at GCSE, right? But on the other hand, we then looked at non-metals. And so non-metals are the ones that are variable. And again, it just depends on the electronic configuration, the number of valence electrons that it has, coupled with the fact it's a non-metal, so higher electron negativity, lower ionization energy, higher nuclear charge means that it can actually take in valence electrons and fill that subshell up, yes. Or on the other hand, it could lose them. All right. So the other one, I think I need to add one more tile in here. The other one, chemists, is we're talking about variable oxidation states. Okay, variable oxidation states. Right. Yeah, let's look at transition metals. Now, the reason why I point out transition metals, chemists, is because in year 13, you obviously do the module, it's like transition metals as aqueous ions. Okay, you got this one. You also will use this when you do redox titrations, when you do the module on pH calculations. Okay, and so there's quite a few examples of transition metals with variable oxidation states. So looking at my trusty iPhone here, okay, let's go look at iron. And so iron, all right, it's got 26 valence electrons. And so I am looking at it being argon, right? Argon, like so. What, 4s2? And 3d, 1, 2, 3, 4, 5, 6. Right, 4s2, 3d, 6. Okay, so here we are then. Now, chemists, if you need to go back and you need to learn how to write the electronic configuration of D block elements, well, then do that. But what I did is I always write it in order of increasing, it's known as increasing principal quantum number, right? And so you're thinking, yes, let me put the fourth one on the outside that's higher in energy and the 3D on the inside because that's low in energy, because you know the energy of the subshells, the shells, they go up in order of increasing principal quantum number, right? So 3 is lower than 4, right? Now then, you're thinking, well, the only one I hear of iron is Fe2 plus, and that's true. Fe2 plus is where I removed 2 valence electrons, these 2 on the outside. And so you're thinking, yeah, this one, I'm going to remove these 2 valence electrons here. And so I end up with 3d6. Yeah, this is iron. That's a 6. Right. Iron 2 plus. Or I could have iron 3 plus, which is going to be argon 3d5. Now then, you're thinking, half-filled D subshell, nice and stable. So therefore, iron 3 plus is a good one, right? Now, would I go lower than Fe3 plus? Like, for example, could I have Fe8 plus? Like I removed the extra 5D subshell valence electrons. Answer, no. Why not? Because even though theoretically I could, problem is that the 3D subshell being half filled is actually stable. All right, so we've got this one, and I'll do one more because I do want to move on and show you how to determine oxidation states. Now, so they like to put the iron on. They like to put the iron on the table right there on the exam, and the other one that you may see, and there's quite a few. I'm just taking a look at this one. Oh, let's do chromium element 24. All right, so chromium then, hold on. So chromium is going to be argon like this, and what, 3D 1, 2, 3, 4, argon 3D 4, 4 is 2. All right then. Now you're thinking, what's a possible oxidation state of chromium argon? 1, 2, 3, 4. Yeah, well, I could have, right? And chromium has lots and lots of variable oxidation states, along with all the other transition metals, right? So I'm just going to pick out the common one that you will see, because where do these variable oxidation states come from? Well, they come from the fact that you're just picking off valence electrons. All right, so one that is stable, all right, because you could have chromium 2 plus, yes. One that is stable is chromium 3 plus, which is argon 3d3. And another stable one is chromium 6 plus, which is just going to be argon. So what I'm saying is the transition metals, you know, you got iron 2, you got iron 3. Could you possibly go all the way up to iron 8 plus? Absolutely. You could remove the valence electrons in this D subshell. Same thing with chromium. You could have, you know, chromium plus 1, chromium plus 2, all the way up to chromium plus 6. The stable ones seem to be plus 3 and plus 6, so right? So what I'm getting at is this, is that you do need to have an idea that non-metals, a real option on, non-metals and transition metals have a variable oxidation state, and this oxidation state is dependent upon the electronic configuration. and, you know, the interplay between electron configuration, nuclear charge, electron negativity, ionization energy. Yeah. So moving on, let's have a little look then, all right, at how you actually determine one of these oxidation states. So let me pop back into Air Force Blue like this. Right. So, and I'll work with these with you. The reasons I picked these chemists is because, look, he's got chromium, yeah, which is the popular one, along with manganese, which is the popular one in year 13. You got some anions over here. Let me start out with this one, Na2CO3. So you've got N, take off fuller option, right? I've got Na2 like this, CO3, right? Now, over here then are common oxidation states, like ones that just tend to be fixed and they tend to occur all the time. So common oxidation states. And we'll build these up as we go along. So the first one is fluorine. Only has one oxidation state in its ion. It's fluoride, F-1. All right, so this one is going to be obviously -1 charge. And I know what you're thinking, yeah, but hold on a minute. Didn't you just say that non-metals have variable oxidation states? Well, fluorine is a non-metal. I mean, how come it can't be -1 all the way down to +7 like chlorine was? Because fluorine is so electron negative, all right? You're thinking it's extremely electron negative on the Pauling scale, number one. Number two, very low, very high ionization energy, very small atomic radius, really high nuclear charge. Guess what? It's not going to give up valence electrons. It's only going to accept them in. And so fluoride, -1 is the only one you'd see. The other one then is oxygen. Now, oxygen, all right, well, you can either have it be -2. Let me draw it like this. Let me actually draw oxygen like this. And so you're thinking, right, so here's my oxygen. Right? So I'll put oxygen like this. Well, it could be -2 or it could be -1. And you go, yeah, well, hold on a minute. I mean, how do you know? Like this one over here, like sodium carbonate. I mean, how do you know if it's -2 or -1? Simple. Now, look, chemists, all I do is I just keep a few things straight in my mind. All right. And I say to myself, right, so oxygen in -1 state. The only time you would see this is if it is a peroxide, as in H2O2. All right, so this is going to be a peroxide. And the other one is if it's an oxide. And so when I think of an oxide of oxygen, I just think of water, H2O. Yeah, you know, keep it simple, chemists, right? Because you know hydrogen, well, hydrogen only has one valence electron going around it. So you think around its nucleus, you're thinking, yeah, this has to be +1. Makes sense. Therefore, oxygen, an oxide, has to be -2. Right. If I use the same logic down here, then hydrogen has to be +1. And so the total positive charge, because there's two of them, would be +2, which means that the oxide total on the right-hand side would have to be -2, which means each one has to be -1. So if you come over here, then I can say with confidence, I can say, yeah, there is no earthly way that I can make this look like a peroxide. It's an oxide, you know, carbonate, oxide of carbon. And so therefore I can say this is -2. And sodium, well, you know, sodium is in group 1. So therefore it is a +1 charge like this. It's in group 1. Right. Oh, look, here we are. right? Carbon is in, I'll do this, my favorite color. This is what I call Kermit the Frog green. Right there. This is what I call Kermit the Frog green. Look, carbon has to be the variable one. Why? Well, because it's a non-metal, it's on the right-hand side. And so do you notice, by the way, that there isn't a charge here? There's no charge on the compound. Yeah, like you see over here, like the MnO42 minus, right? Okay, then. So I'm going to say, well, 2 sodium, so 2 at +1, yes, plus 1 carbon, whatever that is, variable oxidation state, plus 3 times -2 for my oxygens must equal 0. Right. Okay. Well, 2 plus my 1 carbon, minus 3 times 2, 6, equals 0. And so therefore, using my advanced math skills on this Sunday afternoon here, I make carbon equal +4. Now, chemists, what I do is, after I do this, is I stop a minute and I think, yeah, did that make a bit of sense? Yeah, I think so, because carbon has 4 valence electrons, and so therefore being positive 4 could be a possibility. All right. What I mean by that is, if you do the calculations, let's say you had carbon be +6, you go, oh, hold on a minute, it can't be +6 because there's only 4 valence electrons, right? Yeah. So here we are then. So this is this one. So on this one, we said carbon is 4 and oxygen is -2 and sodium is +1. All right, then. Let's do another one. All right. Let's do this one here. All right, Cr2O3. All right, then. So straight line, back into Air Force Blue. I do like the colors a bit paper gives us. It's nice. Right, so look, here we are then. See, take off ruler option, hold on. Could I do it live? You know, right. Cr2O3, Cr2O3. So again, straight off, I notice there's no charge in the compound. And the reason I mention that is because next thing I'm going to say is well, oxygen, there is no way oxygen can be a peroxide of -1. So oxygen is worth -2. Obviously, chromium is my transition metal, so it's my variable. And this one, so I got 2 chromiums. I got 2 times chromium like this, plus 3 times -2 is 0, adds up to the charge in the compound, which in this case is 0, right? So I've got 2 chromiums, wherever that is, 2 chromiums, -6 is 0. And so, all right, I got chromium being +3. Now again, stop, a little think now, you go, yeah, does that make sense? Actually, it does, because we looked at the electronic configuration of chromium, right? You're thinking, yeah, it could lose 3 valence electrons and be chromium +3. Absolutely. Right then. You go, Now, the first example we did was the one where we just looked at a group 4 element as our variable. And then we moved in, like a non-metal. And then we moved into a transition metal. Right. Now, meanwhile, chemists, let's come down to here and let's have a look at one where I'm using a transition metal, but it's got a charge on it. All right, then, here we are. back into this one right here, Air Force Blue. I love Air Force Blue. All right, very nice color. All right, so here we are. I've got Mn. I can take a little option off. Hold on, chemist. I've got MnO4 2 minus. All right, this one here. Okay, so first off, what I notice is I notice that the charge on my ion, -2. See up here, these were just plain old compounds, right? And so they would be neutral, but pure charge on my ion is -2, which means that whatever charge is like determined for the manganese and the oxygen, when I add them together and sum everything up, they've got to equal -2. So here we are then. So we know by now, yeah, oxygen has to be -2 because it isn't a peroxide, is it? No, like, you know, H2O2 or any other kind of oxide like that. No, it's just a plain old oxide of manganese, -2. So I've got one manganese, whatever that is, one manganese like this, and I've got 4 oxygens, so 4 times -2 equals -2 charge on the ion. Right, so 1 manganese minus 4 times 2, -8, equal to -2. And so am I thinking that manganese, right, use my advanced math skills on a Sunday afternoon, I'm thinking that manganese then has to be +6. Now again, if you look at your periodic table, all right, and you write down the electronic configuration for manganese, you'll find out that yes, it could possibly lose 6 valency electrons, which means that this is a possibility. So again, it's just a common sense check, chemists. Like, for example, if you had to say manganese be, I don't know, -2, you go, hold on a minute. Metals don't have a negative oxidation state, that a negative charge, they're always positive. Right, so common sense check, right? This is +6 right here. And we'll just do the last one right here, and then we'll move on to do something else. Covering quite a bit of ground today for my year 12 chemists. All right. All right, hold on, I gotta get this lined up just about right, like so. All right, back into navy blue. Yeah, all right. So MnO4 minus. Take this ruler option off, MnO4 minus. All right, again, as a charge my ion. Hold on, charge on ion. So I've got, well, I'm picking up on the fact that manganese has to be the variable oxidation state. Why? Because it is a transition metal. 1 manganese and 4 oxygens at -2 are at equal -1. And so manganese, right, -8, that's supposed to be an N -8, all right, is -1. And so manganese has to equal to +7. And again, if you looked at the electronic configuration of manganese, you would see, yes, it could be +6, absolutely, or it could be +7. And we're not surprised by that because it's a transition metal. We know that non-metals and transition metals can have a variable oxidation state. All right. So anyway, on this one, chemist, let me by title on this one. This one here is quite simply determining oxidation states like so. And it's going to be very handy in this lesson, the next lesson, year 13, Absolutely, like so. All right then, so having said that, yeah, look at the time. We've just got some time to do these. All right, chemists. All right, here we are. So this one is quite simply, this is going to be balancing half reactions in acidic media. So we'll start off with these. Next time, I'll show you neutral, I'll show you acidic again, I'll show you alkaline, I'll show you how to deconstruct the redox equation into two half equations, balance it, and then put it back together again. All right then, so over here then is just a few simple rules right here. So if I look at this one, then I'm going to follow the rules directly. So I'm going to just one last time, probably in orange. Now, I don't know if you follow American football, but you know, this one to me, is it like Syracuse orange? Is that the one? Anyway, it's a nice, very nice shade of orange there. So take a look. All right, so here we go. I'm on this one. So we call this example one, like so. All right. I've got hydrogen going into hydrogen ion. So I snap the sigma bond. Right. Now, very first thing I need to do, and just follow the instructions here, I need to determine the oxidation state. Well, again, chemists, well, this is easy, right? This is obviously +1. But something to keep in mind is that the oxidation state of any element in its natural state is 0. So, for example, hydrogen gas is 0, oxygen gas is 0. Notice the word gas, right? Chlorine gas, CO2 is 0. Metals are 0, for example, like silver metal has a 0 oxidation state. Sodium metal has a 0 oxidation state, not the ion, the actual element itself, right? And the natural state has an oxidation state of 0. So, in the very first bit, all right, balance the element, changing oxidation state. All right, we go with this one. Let's see, I'll do it here. Didn't like that dot. Move that dot, hold on a minute. Yeah, I know. So look, hydrogen breaks into 2H plus. Now, I do talk about equation state. Let me talk about that at the end. All right, chemists. And so if I put the oxidation states in, yes. Have I balanced the atom changing oxidation state? Yes. Now, I need to sort out the electrons. I'm on the third pointer right here. Now, chemists, if I'm going from 0 to +1, yeah, what this means is that the hydrogen, this is what I think about, look, hydrogen atom, well, you know, this is just 1s1. So the hydrogen atom has lost a valence electron. There's 2 hydrogen atoms in a molecule like this of hydrogen. Therefore, I've lost 2 electrons. It's 1 electron per atom at the top here. But this is a molecule which contains 2 atoms. Therefore, I've lost 2 electrons. And we're done. This was an easy one, right? Easy. Where's my green pen? Right here. Right, the easy. All right, chemists. Now, this one on the right-hand side, ooh, a little bit more tricky, but follows the same rules, okay? The very first thing is obviously, and I've got to keep everything color coordinated, chemists. All right, I'm going to make this is obviously +3, because this says this +3. Over here then, chromium, have a little think, all right? So sidebar, do sidebar down here. Right, I got Cr2O7 2 minus. Well, I got two chromiums, or whatever it is. Again, it's my transition metal. It's going to be my variable oxidation state. Right, plus 7 times -2 equals -2. So 2 chromiums minus 14 is equal to -2. All right, so you've got 2 chromiums minus 14 is equal to -2. Therefore, I think you would agree the chromium is +6. All right, chromium is +6. All right, now again, we're talking about chromium atom going into chromium ion. Now, thinking about this one, balance for atoms that changed oxidation states. Now, chemists, do you notice, and I'll do loads of these examples next time, right? You're thinking, we never bothered doing this for hydrogen or oxygen because we add those in later. All right, so I've always got 2 chromiums on this side. We've got what? Cr2O7 2 minus arrow. Yeah, 2Cr3 plus like this. Yes, balance the chromiums, the element changing oxidation state, right? Sort out the electrons. Now again, chemists, so I think about it is, look, chromium is +6 and it's going down to +3. So think number line. Let me just do a number line just about here so you see what I'm talking about, right? Here's my number line. Oh, I do like bit papers, very nice. So look, here we are then. +6, +5, +4. Sometimes when you're beginning, it's sometimes good just to see a graphic, right? So look, I'm here at +6, and I've gained 1, 2, 3 electrons, all right, to go from +6 down to +3. So I'm going to add the electrons on the left-hand side. How many electrons do I add? Well, each atom went from +6 down to +3, but there's 2 atoms, which means that I need to add 60 electrons, right? Cr2O7 2 minus plus 60 electrons, arrow, goes to 2Cr3 plus. Right. Now then, that is a R for chromium right there, chemist. Got to balance the oxygens. Now, the way you balance the oxygens is by adding water to the other side. So if I've got 7 oxygens on this side, I would need 7 waters on this side. So I've got Cr2O7 2 minus, right, plus 6 electrons, yes, plus on this side, I've got 2 chromiums and 6 electrons goes to 2 chromium 3 plus, and I need to add 7 waters to this side to balance out the oxygens, right? 7 oxygens here, 7 oxygens on this side. But now I need to balance out the hydrogens. So on this side, I've got 7 times 2. All right, 7 times 2, here's my 14 hydrogens. Because up here, I got 7 oxygens, which is why I added 7 waters, right? I'm trying to get arrow go a little bit better here to the oxygen. Right then, so here we are. Cr2O7 2 minus plus 6 electrons plus 14 hydrogens, like so. Arrow 2, supposed to be a 2, Cr3 plus, and 7H2O, and 14 hydrogen ions, right? Voila, we are done. So look, figured out the oxidation state, +6, +3. This was given. This one, we figured it out using the skills we learned the previous tile. Balance for atoms that changed oxidation state, 2 chromiums, 2 chromiums. Added in electrons, think number line to figure this out. We get started. We go, right. It's a change of 3 electrons per atom. 2 atoms is +6. And then you're thinking 7 oxygens on this side, 7 waters on this side, 14 hydrogens on this side, 14 hydrogens on this side. So hold on, I got that was just a carry from up here. Right, now begin to wrap, chemists. This seems to be a good point to wrap, but look, you do need to put in equation of state. And I'm going, oh yeah, but oh, come on, do I have to? Yes, you do. Why? Well, because sometimes the mark scheme wants you to put an equation of state. Sometimes the mark scheme doesn't want you to put an equation of state. And I always talk about bandwidth, meaning that, you know, when you're taking the test, you're thinking, oh, I've got to recall how to do so many different skills and strategies and memorize this and that. And I'm really stressed out and whatever. You got all this stuff in your mind. Well, you don't need to be adding in anything else extra. Like, do I need to add an equation of state? Do I not add an equation of state? I always add them in. And then if the mark scheme wants it, great. If not, well, don't worry about it. So here we are. Hydrogen is obviously a gas. This is obviously going to be aqueous. It's going to be inside solution somewhere. Over here, aqueous. Actually, I always just do it at the very end, like the very last one. So when you're working these out, like next time, you know, when we're doing balancing in acidic media, taking them apart, alkaline media, yeah, very last line put in. Now, chemists, please make sure that water is a liquid. Yeah, this is not philosophy class, meaning you're thinking, well, if what done water is aqueous, well, the next question is, well, what's it dissolved in? Itself. What? No, it doesn't make any sense. All right, so chemists, looking at my clock over there, right? I got 5 past the hour, so we did well today. Now, what I'm thinking we'll do next week then, right? Next week, same time, same channel, is we'll look at redox reactions. We'll go into a bit more depth. All right, we'll balance some more half equations, which is what this is, right? Number 1, I'll show how to put them together to form a whole equation. Number 2, then I'll show you how to take them apart and balance each side and then reconstruct it. And then probably like the end of like the next lesson, what we'll do is we'll take a look at balancing more difficult equations, because they do go into fractional oxidation numbers. Yeah, I know. Really? Is that on the spec? It is, if you look very carefully. All right. And I'll show you how to balance in alkaline media. All right. So chemists, that does indeed wrap it up for today. All right. You have a good day. You have a good week. And I will see you next time. All right. So take care.